Hello, space enthusiasts and curious minds alike. Today, we're diving into the real science behind the James Webb Space Telescope, often abbreviated as JWST. You've probably seen a lot of sensational claims and speculations about Webb's findings, but let's cut through the noise. Join me as we explore the three biggest genuine discoveries made by JWST, breaking down the facts without the fluff. Have you ever been mesmerized by those breathtaking images of galaxies in astronomy books? Most likely, they were captured by the iconic Hubble Space Telescope. For decades, Hubble has been our window to the wonders of the universe, offering profound insights into the cosmic ballet. However, in 2022, the baton was passed to the James Webb Space Telescope, JWST, marking a new era in space exploration. The JWST isn't just a souped-up version of its predecessor, it's an entirely different beast. Engineered to detect infrared light, Webb can unveil galaxies, billions of light-years away galaxies that would otherwise remain hidden from us due to the redshifting of their light, a phenomenon caused by the ongoing expansion of the universe. Since its deployment, the James Webb Space Telescope has been busy rewriting the cosmic rulebook. From uncovering the most ancient galaxies to probing the mysterious atmospheres of distant exoplanets, Webb is expanding the frontiers of our knowledge in unprecedented ways. Yet, amidst these groundbreaking discoveries, there's a swirl of misinformation and over-the-top headlines that often distort the real science. In this video, we'll cut through the noise and focus on some of JWST's most groundbreaking findings and their implications for our understanding of the cosmos. Get ready to dive deep into the heart of our universe as we explore these monumental discoveries together. I'm here to give you the unvarnished truth, no frills attached. If you're as thrilled as I am about the James Webb Space Telescope, JWST, you'll want to keep watching because we're diving into that right now. While the Hubble Space Telescope has provided us with some spectacular snapshots, it primarily captures images across the near-infrared to ultraviolet spectrum, much of which falls within what we humans see as visible light. This is fantastic for photographing cosmic entities in familiar colors, but here's where we hit a snag. A galaxy that's relatively close to us might appear vibrant and detailed because it sends its information through visible light. However, imagine a galaxy billions of light years away. To us, it would appear drastically different, not due to any physical alteration, but because the light it emits has been stretched to wavelengths longer than what our eyes can perceive, a phenomenon known as redshifting. This space-time stretch elongates the light's wavelength as it travels, and for very distant galaxies, this redshift means we receive light that falls below even the infrared spectrum. This is precisely why the JWST is such a game changer. Not only does it surpass Hubble in size and capability, but it is also exquisitely equipped to observe these distant celestial bodies, capturing details of the universe never seen before. Let's explore how this incredible technology is opening new windows into the cosmos. The James Webb Space Telescope, JWST, was engineered with a very specific mission in mind: to capture the cosmos in infrared. This intricate focus on infrared imaging is precisely why many of the photos you see from Webb have colors added in post-production to translate its findings into visuals that our eyes can comprehend. Without these enhancements, the original images would be invisible to us. So, has the James Webb succeeded in its mission? You might say it's exceeded expectations, perhaps a little too well. Once Webb began sending back its first images, the scientific community was set abuzz. Physicists rushed to analyze this new wealth of data, sparking what can only be described as a frenetic dash. Researchers raced against each other, each eager to claim the discovery of the oldest galaxy. This frenzy was, in many ways, the whole point of investing billions into Webb. However, as the initial excitement settles and we take a more measured look at Webb's findings, a complex picture begins to emerge. It seems increasingly likely that our results are either misinterpreted or And this is a thrilling yet daunting thought. There might be something fundamentally amiss with our understanding of the universe. Our current cosmological model, known as Lambda CDM, lays out expectations for the universe's evolution post-Big Bang. But what Webb is showing us might just challenge some of these foundational assumptions. Let's dive into how this incredible tool is not only capturing images, but also potentially rewriting the very rules of the cosmos. In the infancy of our universe, primarily a vast expanse of hydrogen gas, it was not a perfect uniform soup. Tiny quantum fluctuations meant that this gas wasn't evenly distributed. This set the stage for the mysterious and unseen dark matter, along with gravity, to begin sculpting the cosmos. They pulled hydrogen gas toward regions where it was slightly denser. These are what astronomers call overdensities. About 200 million years after the Big Bang, these local pockets of hydrogen gas grew so dense and hot that they sparked into life as the first stars. This was just the beginning. From these initial stars, more began to form, and soon they clumped together into vast cosmic cities of millions and billions of stars galaxies. Over time, these galaxies gathered into even grander structures, galaxy clusters and superclusters, painting a complex cosmic web across the dark canvas of space. This process, starting from a mere sea of hydrogen and culminating in the magnificent structures of galaxies we observe today, charts the structural evolution of the universe. However, there's a hitch in our current understanding. According to our models, forming big, bright galaxies like the ones we see today should take a considerable amount of time. It's a hierarchical dance of gas clouds condensing gradually over eons, stars forming and flocking together into galaxies. Yet, what we see challenges this timeline, suggesting that perhaps our grasp on the cosmic narrative might need revising. The brightness of a galaxy typically tells us about its star count or mass. However, the James Webb Space Telescope has thrown us a cosmic curveball with its discovery of JWST Zone 140, the most distant galaxy identified to date. Surprisingly, this galaxy blazes with a brightness that, according to our theories, shouldn't exist so soon after the Big Bang, less than 300 million years, to be precise. We're rigorously double-checking our findings, but as it stands, this discovery challenges our current cosmic blueprint. Is there a fundamental flaw in our understanding of cosmology? Does this finding imply that the Big Bang model is incorrect? While it's tempting to leap to dramatic conclusions, the reality is less sensational. Despite headlines that might proclaim the demise of the Big Bang theory, such statements are misleading. The real big discovery here is that early galaxies like JWST 140 were more mature than we anticipated. This enigma presents an exciting challenge for astrophysics, pushing against the boundaries of our established models of galaxy formation. Far from being a setback, this anomaly is a boon for science, nudging us towards a deeper, more nuanced understanding of the universe and refining the Lambda CDM model. The physics community is already abuzz, with several studies underway that aim to reconcile these startling observations with existing theories. The recent discoveries made by the James Webb Space Telescope have us poised on the brink of developing a new and improved model of the universe. One intriguing possibility to explain the early formation of galaxies is that our understanding of dark matter might be flawed. Since dark matter is thought to form the structural backbone of galaxies, any unexpected properties it possesses could drastically alter our predictions. To date, no dark matter particles have ever been directly detected, leaving us somewhat in the dark about its true nature and behavior. Another exciting avenue involves dark energy. Some models suggest that an early dark energy field might have existed in the nascent universe, potentially altering the mechanics of early universe dynamics enough to account for rapid galaxy formation. Further theories propose the existence of population 3 stars in the early universe. These supermassive stars, nearly devoid of any metal content, would burn fiercely and briefly, ending their lives in supernova explosions that lead to the formation of early black holes. Such dramatic ends could accelerate the evolution of galaxies, providing the necessary conditions for more advanced cosmic structures to emerge earlier than our current models predict. Each of these hypotheses represents a piece of the cosmic puzzle we are diligently working to solve, as we strive to align our theories with the mesmerizing realities being unveiled by modern astronomy. While we continue to grapple with the mysteries of the early universe, there are numerous theories in play that might untangle this enigma. These aren't necessarily groundbreaking upheavals in physics, but rather subtle tweaks to the established lambda CDM model. Switching gears, I'd like to share something a bit different today, a fantastic tool that's been immensely helpful in my own research. I'm talking about a groundbreaking app called Listening.com, which has graciously sponsored this video. This innovative app transforms academic papers, my usual reading material for crafting content like this, into audio formats. This allows me to absorb information on the movie, enhancing comprehension and efficiency. Listening.com isn't limited to academic papers. It also converts textbooks, PDFs, websites, and even emails into spoken word, making it possible to engage with complex material while driving, working out, or handling other tasks. What sets it apart? It's adept at reading mathematical equations, automatically skipping over citations and footnotes, and it even correctly pronounces challenging technical terms. Plus, it smartly identifies chapters for easy navigation, and you can choose from a variety of voices to suit your listening preference. For anyone who consumes as much research as I do, you'll likely find Listening.com a game changer. Curious to try it out? You can download the app for free, and by using my special link, you'll receive an exclusive offer to enhance your listening experience even further. Now, here's an exclusive deal just for you. Click the special link in the description to get an additional week free on Listening.com. Don't miss out on this opportunity to transform how you access academic content. Now, let's dive back into some of the most thrilling discoveries made by the James Webb Space Telescope, JWST. One particularly fascinating capability of Webb is its unique perspective on the evolution of supernovae. In a stunning demonstration of its capabilities, JWST captured an image of the same supernova at 3 distinct points in time. While this might sound like something out of a sci-fi novel, it's a real phenomenon made possible by gravitational lensing, a concept predicted by none other than Albert Einstein over a century ago. Gravitational lensing isn't new, but JWST's advanced optics and its ability to observe distant objects have taken it to a whole new level. Essentially, this technique works much like the lens on a camera, magnifying and focusing distant celestial phenomena for a closer look. However, JWST has an extra trick up its sleeve. It can use massive galactic objects as natural cosmic lenses, exploiting their immense gravitational fields. These massive celestial bodies warp the fabric of space-time enough to bend the path of light passing near them, acting like a gigantic magnifying glass in space. This incredible phenomenon allows JWST to capture images that would otherwise be beyond our reach, offering a glimpse into the cosmic ballet of stars and galaxies unfolding over billions of years. One captivating example of gravitational lensing at work is the supernova AT 2022R, located about 9 billion light-years away. This supernova sends out light in all directions, and in an empty universe, we'd see a single image from 9 billion years ago. However, our universe is teeming with massive objects that can bend light. In this case, a galaxy cluster named RxJ 2129, situated 3.2 billion light-years away, lies between us and the supernova. The mass within this cluster is unevenly distributed, causing the light from the supernova to bend along different paths. This alignment results in the light taking multiple routes to reach us, producing 3 distinct images of the same event at different times. The light that took the longest path shows the oldest image of the galaxy with the supernova still visible. The second image captures the galaxy about 320 days later, and the final image reveals the scene 1,000 days after the first. Thanks to the JWST's near-infrared camera, we can witness the progression of this supernova in a single shot, offering a unique glimpse into its evolution over time. In the latest images, the supernova has already faded from view in 2 of the frames, so we didn't gather much new data. However, this demonstration showcases the remarkable power of the JWST and the potential of gravitational lensing to zoom in on a single object in the universe and observe it at multiple points in time. This capability could be incredibly powerful for future astronomical studies. But that's not all the JWST excels at. It's also a game changer in the identification and analysis of exoplanets, including determining their chemical compositions. In fact, the telescope is so advanced that it has managed to capture direct images of several exoplanets, though that's a story for another time. What's truly revolutionary is how the JWST can ascertain the chemical content of these distant worlds. This process is fascinating. By leveraging the knowledge we've gained on Earth, we can study phenomena far beyond our planet. One core principle of physics is that the laws of chemistry and physics are consistent throughout the universe. While the conditions on various exoplanets will differ, the fundamental laws remain the same. Thus, by studying chemicals and their properties here on Earth, we can apply that information to analyze the atmospheres of exoplanets, uncovering their secrets from light years away. To identify these same chemicals elsewhere in the universe, we focus on light absorption. By studying a star's light spectrum, its emission of blue, green, red, etc., we can gather essential data. When an exoplanet orbits this star and passes in front of it from our perspective, it causes a dip in the star's luminosity. This is a common method for detecting exoplanets. Here's where it gets fascinating. If the exoplanet has an atmosphere, some of the star's light will pass through that atmosphere. As the light interacts with the atmospheric chemicals, it leaves telltale signs that we can analyze to understand the atmosphere's composition. By examining the light from the star and subtracting the light that passed through the atmosphere, we can identify the absorbed wavelengths and match them to known chemicals. This technique has already revealed intriguing findings, such as the presence of methane and carbon dioxide on an exoplanet named K218b, located 120 light-years away in the habitable zone of its star. This was the first time carbon-based molecules were discovered on an exoplanet within a star's habitable zone, marking a significant milestone in our quest to find potentially life-supporting worlds beyond our solar system. The composition of K218b hints at the possibility of a water ocean beneath its hydrogen-rich atmosphere. Fascinatingly, initial observations by the James Webb Space Telescope, JWST, detected dimethyl sulfide, DMS, on this planet, a molecule that on Earth is produced almost exclusively by life, primarily by marine phytoplankton. This tantalizing hint suggests the potential for life on K218b, though it could also have a natural, non-biological origin. While this discovery comes from just one exoplanet, similar studies have found other intriguing chemicals on different exoplanets. In my opinion, it's only a matter of time before JWST detects compelling evidence of life on another world. The JWST has revolutionized our understanding of exoplanets. It recently provided detailed chemical fingerprints of exoplanet atmospheres. This data includes detections of water vapor, carbon dioxide, and possible signs of methane, an indication of complex atmospheric processes. These findings are crucial because they help scientists assess the habitability of other worlds, significantly refining our search for life beyond Earth. One of the most anticipated goals of JWST was to observe the first galaxies formed after the Big Bang. Success came stunningly as Webb captured light from galaxies that appeared just 250 million years post-Big Bang. This data not only pushes back the timeline of galaxy formation, but also offers insight into how early galaxies influenced cosmic evolution, challenging our previous models. JWST JWST's powerful infrared capabilities have allowed astronomers to witness cosmic clashes in unprecedented detail. These events, where galaxies collide and merge, are fundamental to our understanding of galaxy evolution. By studying these mergers, Webb provides a clearer picture of how stars and black holes grow, influencing the structure of the universe. In a groundbreaking study, JWST has also mapped the distribution of dark matter in the universe more precisely than ever before. Using gravitational lensing, a phenomenon where massive clusters of galaxies bend light from objects behind them, Webb has outlined how dark matter structures grow and evolve. This is vital for understanding the skeleton of the cosmos upon which all other matter is built. Finally, JWST has shed light on supermassive black holes and their early presence in the universe. By observing quasars, luminous objects powered by black holes in distant galaxies, Webb helps explain how these monstrous black holes formed and grew so quickly. This insight is key to understanding the relationship between galaxies and their central black holes. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blessovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.